Yeah, that's good. Okay, so how's everybody doing? How did it go with Simon 3? A lot of chatter, some of it panic sounding on Sunday night on the forums. Hopefully most of you got things sorted out. But again, I mean, like I said at the beginning of the course, the trick is to submit early and submit all. Not having things that don't compile at all on Sunday night is not a good situation to be. Okay, so last class we had finished talking about scapegoat trees, and we had started looking at these things called trees. And the idea of trees was that we would try and leverage this theorem about so-called random binary search trees. So random binary search tree is what you get when you take a random permutation of n distinct values. Let's say the integers 1 through n. They're usually a good stand-in for n distinct values. Take a random permutation of those and you insert them one at a time into a binary search tree. So we saw, an example that if you have 15 of those values, something like there's one permutation that gives you a big long list, and there's about 25 million permutations that give you a perfectly balanced tree. So it seems more likely that you get balanced trees when you do this. And indeed, there's this theorem that says, in a random binary search tree, you take any value x that you're interested in, and the expected length of the search path for x is at most 2 times the natural logarithm of n. And that was about 1.38 times the binary logarithm of n, and 1 times the binary logarithm of n is about the best we could ever hope for. And now, that's great. It tells you something about the case where you build a tree by inserting a random permutation of values. But, I mean, we want the general case where somebody's telling us what to insert, telling us what to remove, searching for different things. We want to be able to handle that, and that's where trees come in. And trees are a randomized data structure, the same way that skip lists were. And in a sense, they're trying to use the same trick. So if you remember when we defined a skip list, we said, well, what you do is you start with a list with n items, and you toss a coin for each item, and that determines whether it goes up in the list. And then we studied the resulting structure that you get from that thing. But really, that's not the way skip lists are built. Skip lists are built by repeatedly inserting and deleting or deleting things. And it just happens that actually, whether you start with a whole list of things and do this coin tossing experiment, or you use the insertion or deletion algorithms, the lists that you get look the same. You get the same distribution over lists. If I showed you a skip list, you couldn't tell me by looking at it what order the things were inserted in, or even whether it was maybe built the other way by starting with all the elements in one list and tossing coins. And we want to do the same trick here with trees. We want to build a tree that you can add and remove things to, but if you look at it at any given time, you couldn't tell the difference between that thing and one of these random binary search trees that was just built through by doing a random permutation. So a tree stores a set of values, keys. This is the stuff we're trying to store. And it also maintains priorities. So for each key, there's an associated priority. And that's just there to help us make this thing look like a random binary search tree. And it's a binary search tree on the keys, and it's a heap on the priorities. And heap on the priorities means that the minimum priority is at the root. And that's also a recursive property as well, which means so that it holds for every subtree, the minimum priority of that subtree, sort of the root of that subtree. And we saw last class that means if I tell you the keys and I tell you the priorities, and they're all distinct, then you can tell me exactly what the tree looks like. Because there's no choice for the root. The minimum priority has to go at the root. After that, there's no choice about what goes to the left or to the right. Everything that's smaller than the root key has to go to the left subtree, and everything that's bigger has to go to the right subtree. And then recursively, the roots of those are defined are unique and so on. So there's only one tree once I give you the keys and the priority, the parent of keys and priorities. Okay. So does anybody want to ask for clarification about that now? Yes? No, I just forgot to put it in to make it read with priority 0.6. Good catch. Yep.
How long does it take to, let's just say you have a randomly, you have all the elements up there in a row.
Yep.
How long does it take to make the tree?
Well, so you don't get the elements. For a tree, these elements will come by insertions and you'll do something else. But the same question is you could ask, how long does it take to make a random binary search tree? So if I give you this permutation of 1 through n, how long does it take me to insert all those elements into a binary search tree? It's sort of the same question because you can build a tree the same way. And the answer is you can build one of these things. And we'll log in. And the number of comparisons you do is 2 times n log n. And the way you build it is you just insert the things in the order they come. The theorem says if I have a tree that contains a random permutation of some numbers and I search for some other number x, then the expected length of the search path for x is the logarithm, 2 times the logarithm of the number of elements in the tree. And now the only extra piece of information here is that if I have a random permutation and I only look at the first, k elements of that permutation, well, that's also a random permutation of those k elements. So the theorem holds even as you're building the tree. So the first element, once I've inserted 50 elements, what I have is a random binary search tree with n equals 50, and inserting the 51st element, I know how long that takes by this theorem. 2 times the natural logarithm of 50 plus 2. And so you add all that up, and that's n times something where each of those somethings is at most log n, so you get n log n running time, and you can even add up the comparisons really carefully and get that 2 times n1 in comparisons. So you can build this thing in n log n time. In fact, what we will see is this thing here, building this thing, is actually the quicksort sorting algorithm. That's all quicksort does. We'll look at that and we'll see that the quicksort, the famous quicksort sorting algorithm, is building a random binary search tree. Okay. Go back to the tree picture. Any questions? Clarification? I hate when a topic goes across 2 classes like this. I don't mind pausing to answer questions. Okay. Pick these random. And we saw that if the tree is uniquely defined by this set of priorities, but another way to look at it is it's the binary search tree that you get if you took these keys and priority pairs and you sorted them by the priorities. So in this case, it's the binary search tree that I would get if I first inserted 4, and then I inserted 5, and then I inserted 2, and then I inserted 1, and then I inserted 3, and then I inserted 6. Right? Because the priorities are 1 on 4, 3 on 5, 4 on 2, 5 on 1, 6, and 7. So same set of keys and priorities, just sort them instead of by key value, sort them by priority value. And notice that if I insert these things into a binary search tree in this order, I get exactly the same tree. That's sort of easy to see because, well, the smallest value has to go at the smallest priority is the first thing inserted, so it goes at the root. And then recursively on the left and right, well, the first thing that gets inserted on the left will be the one with smallest priority among all these keys. So that the same, you get exactly the same structure. Okay, so two views of this thing. Either it's a structure that satisfies these two properties, or it's what you get if you insert by priority values in the search into a minor search tree. And if you pick these things at random, that means this thing is a random binary search tree. Okay. So in this theorem here, I can replace random binary search tree with the word tree. So I pick the priorities at random, and then I sort by priorities, and I get a random permutation of the keys. And well, that's the tree that I get is as if I inserted the keys in that order. Well, that's the definition of a random binary search tree. So a tree has exactly the same property that the expected length of the search path or anything is at most 2 times the natural logarithm of x. So far, so good? Yep.
Would you have like your extreme take off those priorities in the future?
So what do you mean with the lowest priorities?
Like let's say one have the lowest priority, then would you just get a
Yeah, then you just leave it right there at the root. So that can happen. I mean, there is even a very small chance that the priorities end up being the smallest, second smallest, third smallest, fourth smallest, and so on, in which case you insert them in order and you get a big tree that's just a big long path. Now, we saw that actually the probability that that happens is only 1 out of 6 factorial in this case, whereas there's other trees that are much more likely than that. So you rely on the randomization to hope that these bad things don't happen. All right. So now the question is, that's great. All we seem to have done so far is find a very long-winded way to define a random binary search tree again. How do we turn this into a data structure that supports these operations of adding and removing keys, or adding and removing these values here? Well, for that, we need to know about a very useful and important operation on binary search trees, and that's the operation of rotation. So here's a very abstract picture of a little subtree rooted at y inside of a binary search tree. And here's another abstract picture. A subtree that contains all the same values, everything in subtree A, everything in subtree B, everything in subtree C, plus the two nodes x and y, but it's shaped differently. It's got a slightly different shape to it. In this case, x is the parent of y, and in the other case, y is the parent of x. And if we look at this thing, so the question is, well, is this really something you can do to binary search trees? Well, let's take a look. If we look at this tree on the left here, the binary search tree property says that everything in A is smaller than x. everything in B is bigger than X. Now Y is bigger than all of that stuff. And then everything in C is bigger than Y. So this is what we know about the keys in this tree that follow this order. Everything in A is smaller than X, which is smaller than everything in B, which is smaller than Y, which is smaller than everything in C. And if we look at this search tree on the right here, it's fine, right? Everything in A is smaller than X, everything in B is bigger than X, but smaller than Y, and everything in C is bigger than Y. So if this is a binary search tree, meaning that all the keys are obeying this left-right property, then so is this. And so we call this a right rotation. It's an operation that we can do to Y that allows us to change the shape of this binary search tree that still preserves the order. And of course, this picture is kind of symmetric. We can go back in the other direction. And this is called a left rotation. In this case, it's the left rotation around X. And I don't know that rotation is the best word for it, but it's now terminology that's 40 years old or more. But you can kind of sort of see it as a rotation. Right? I take Y and X and I rotate them a little bit and get this tree here. Of course, all kinds of other weird things happen. Some trees attach to different things, but you know, it's easy enough to remember. You rotate it. Think of this edge here as a thing that's rotated right, and then it's rotating left in the other direction. Okay, so that's an operation that we can do to binary search trees that preserves the fact that they're binary search trees, and it also has a nice, it changes their shape a little bit. Like for example, if we look at A here, before, to get to subtree A, you used to have to go through both Y and X. Now to get to subtree A, you only have to go through X. So for example, if subtree A was too deep, getting too far down, then maybe you could do a rotation here. That would bring subtree A up closer. But of course, there's a price to pay because subtree C now used to be able to just go through Y, now it has to go through both X and Y. So of course, there's a price to pay, and for B, there's no difference at all. You have to go through X and Y. In both cases, the order does change. So not that helps. Okay. So these are the restructuring operations that we'll use because we're trying to maintain one of these trees. So maybe the best thing to do then is to just go with an example. Start with a really simple one. Let's insert into this tree here. Let's add the element, the value 5.5. All right. So how do we add 5.5 to this tree? Where would it go? Yep. Okay, so we give it a random priority. I'm going to pick a really random priority. My random priority is 0.8. Okay, so now what? Yep. Yeah. So we'll do the normal thing for inserting into a binary search tree. We'll just search for 5.5 until we fall out of the tree, and that's where we'll add it. So 5.5 is bigger than 4, so we go to the right, bigger than 5, so we go to the right. It's smaller than 6, so we go to the left, and there's no place to go here. We fell out of the tree, so this is where we're going to attach 5.5 with its random priority, 0.8. Now what? Anything else to do? So is this still a tree? 5.5, the key is in the right place, so it's a random binary search tree. It's still a heap? Yeah, because if you look at the edge from any child to any parent, the child still has a bigger priority than the parent, or another way to think of it is every subtree, the root has the minimum priority. The only place where we could have a difficulty with an edge would be this new edge we just created here, but we got lucky and our random priority here was bigger than the one with the parent. So let's try harder. Let's do 3.5. And I'll take some random priority, I don't know, maybe point 0.5 what? All right, so what's the first step then? What's that? Insert it into the tree the normal way. So that means we follow the search path with 3.5, smaller than 4, bigger than 2, bigger than 3. 3.5, along with its priority. 0.51. Are we done? No? What's wrong? The priority is smaller than the priority of its parent, or another way to think of that problem is in this subtree, the minimum priority is higher than in this subtree of 2, size 2. So we need to fix that. How do we fix it? Use a rotation situation. That looks a lot like this picture, right? X and Y. I don't want that situation. I want to have this situation. So I do a rotation. So this is the X in that picture over there. This is the Y. So I'm doing a left rotation to push X down and bring Y up. And after I do that rotation, picture's going to look like this. One. The thing that I just erased was 4, then priority 3, priority 6. X moves down, Y moves up. Okay. Now, are we done? Yeah, we're done because the only place where we might have a problem now is between this node we just moved up and its parent, but in this case we got lucky and we finished. All right, so what's the general strategy then? We did 2 examples. What's the general strategy? Yeah.
Insert
So basically, the algorithm for adding a new value just inserts the normal way, adding this new value as a leaf. And alongside this, you pick a random priority to go there. And now, as long as the priority of that thing is smaller than the priority of its parent, you do a left or right rotation, whichever one is appropriate, to swap the roles of that thing and its parent. And, okay. And so eventually, hopefully this stops. How do we know that this stops? Yep.
What is the smallest priority?
Yeah, eventually, I mean, if we look at what a rotation does, so we're always doing something like taking this node and moving it upwards in the tree, so we're actually decreasing its depth, which means it's getting closer and closer to the root. And the only way it'll ever actually get to the root is if its priority is smaller than that of the root, meaning it's the minimum priority now in the tree. And then once it gets to the root, well, that's where it's supposed to be. There's nothing else for it to do. So basically, as long as you have a parent and your priority is smaller than that of the parent, you move up in the tree. Eventually, you either become the root, or maybe you stop. Usually, you stop before that. All right. So how long is that going to take? Yeah.
The height of the tree and the worst case?
The height of the tree?
The height of the newly added node.
Yeah. So it'll take time. That's the number of rotations you do is at most the height of the newly created node, because or the depth of the newly created node rather, because each time you do a rotation, the depth decreases, and well, it can only decrease till it gets to 0. So the time that this takes is equal to, well, how many steps there were it took you to get down to this thing, which is the depth of the newly created node. And here we have a theorem that says this newly created node has expected depth at most 2 on n. So we can add an element in time as fast as we can search for it. So let me just say, add, we can summarize it. It's just a normal BST add followed by rotation to restore the heap property. So just for example, if when we had inserted 3.5, if we had somehow gotten a smaller priority, like 0.2, just to test your understanding, then what would happen at the next step here? That means we would have this thing being 0.2. Is that a valid tree? No, it doesn't have the heap property. There's a problem here. Small priority as the child, big priority as the parent. We fix that. So we use a rotation, and what kind of rotation? The left rotation. So this is the parent, this is the child. We rotate them left. I'm not going to draw this because then I have to redraw this. So that's what would happen. And if the priority was even smaller still, like 0.05, now we get this thing out to the root of the thing. And then it stops for sure. And let's leave this where it was. It was 0.51. All right. Good. So we know how to add things. We know how to search So I want to remove something from this tree. How would I proceed? Start with something easy. Is there an easy one? Well, let's start with something really easy. What if I want to remove 3? So 3 is a leaf. So I just go and I chop it out. So that certainly isn't going to break the binary search tree property. And well, now there's just less edges in the tree, so that there's not going to be any problem with. I mean, there's no more new parent-child relationships, so all the old ones are still good. They're still good, and we took away this one, so definitely there's no problem there. So removing something, if it happens to be a leaf, it is easy. You just deleted the normal one. What if I wanted to remove 2? Okay, so I want to remove 2, and this is one of those annoying nodes that has 2 children, so it's hard to remove. And so the suggestion is that I do a right rotation of 2. Why? Yeah. So I want to, the strategy is I'm going to do rotations. In fact, I'm going to try and do the opposite of what adding does. Adding does rotations to bring the newly added node up in the tree. Instead, I'm going to use rotations to bring the newly added node down in the tree until it becomes a leaf, and then I can cut it out. So now the difference is, to bring a node up in the tree, there's only one rotation that does it. You have to take its parent, and you have to rotate it either left or right, depending whether it's the right or left child of the parent. But when you're trying to bring a node down, you have 2 options, left or right. Now, remember though, that something is going to replace this node here. And that something should be the smallest priority in subtree. And that something is going to become the root of the subtree that has everything in it. And so you look at the 2 children, one of them has smaller priority, and that's the one you're going to use to replace this. In this case, the left child has smaller priority, so I will do a right rotation to bring the left child up here. So let's draw that in. Okay. 1, 5. So that brings this guy, that rotation there, brings it down 1 level. Now we could actually just splice it out, and that's okay, because, well, so if we splice it out, that means we take this, we just delete it from here, and then this thing goes to its only child down here. We know that that's a safe thing to do in binary search trees, and it's a safe thing to do in heaps just because you have this transitivity that this is bigger than this, which is bigger than, well, it's supposed to be bigger than this. So that would be okay. But I want to go a little further. I only want to delete this thing once it's a leaf. So what would I do now? Not 3.5, but 2. Yeah. So you take 2 and you rotate it left, and that brings 3.5 back up into this place. And gives you this picture. 3.5. 2. 1. That gives you that picture, and now you just cut that edge, and you're good to go. That thing's gone from the picture. All right. So super easy. Just do rotations until the thing becomes a leaf in the tree, and then remove it. So anytime someone tells you an algorithm like that, gives you this is like a while loop, while this node is not a leaf in the tree, look at the 2 children and do a left to right rotation. So the first thing you want to convince yourself is that this eventually finishes. Not an infinite loop. Why is it not an infinite? How do I know that I will eventually become a leaf in the tree? Yeah. I don't like that phrase, most probably. Why? So give me an easy argument that this thing eventually increases. Right? So we're pushing it down further and further away from the root. So it cannot increase to infinity because the worst thing that could happen potentially is that the tree is a big long, at the end of this process is a big long list, but eventually this thing gets to the end of the list. And so after at most, well, if we started at the root and did these rotations, it would be after at most n minus 1 steps, we would get to this thing would be distance n minus 1 from the root. That's the biggest step you can have in any tree with n nodes. So then it's definitely a leaf. Okay? So the running time is not more than order n. It's not, but at least it's not infinite. That's the first step in showing something is efficient, is to show that it terminates. We'd rather show that it's something like log n. How do we do that? This is tricky. Right? Because if you think about it for a little bit, I mean, here's y. Let's say y is the node we're trying to push down until it becomes a leaf. And so in this case, we might do something like a right rotation. So we do this right rotation, and ultimately, we may end up pushing y down until it becomes a leaf in this subtree here. But notice what just happened there. We just pushed this tree down further as well. So we didn't get any closer to being a leaf in this tree. So it's not obvious that the height of anything in this tree is what controls how far you'll have to go for this. I mean, we're somehow getting further and further away. We're not getting any closer to our goal. So at first it looks like it's going to be really non-trivial to see that this is efficient. I mean, in fact, that already shows that you do need an argument to show that it terminates, because here it doesn't get any closer to becoming a leaf in C. So, any ideas on how we could show that this is efficient? Anybody read ahead? So let's go back and look at this picture here, where we just removed 2. Like it's still there. So what if we were go back in right now and insert 2 with the same priority as before, what would happen? Yep. Yeah, we would rotate, do a rotation to bring 2 to here, and then we do a rotation to bring 2 to here. And in fact, those things, if you can play that back in your head, they're exactly the inverse operations we did when we removed 2. So that's not an accident. That will always be the case. That's the reason I wanted to push this thing to actually be a leaf rather than just splice it out right away. So whatever happens when we remove is the opposite of what happens if we insert. Yeah?
So when, since we know how long it takes to do that, so
Yeah, that's it exactly. So this remove operation is exactly the same thing that happens, but in reverse. So removing from a tree of size n is the same thing as adding into a tree of size n minus 1. It's like adding the element that is not there but played in reverse. So you make a little movie of what it would be like to add that element, play that in reverse, that removes it. And well, we already analyzed add. It takes order log n time, and therefore remove does as well. In fact, remove is a little bit faster because it's into a tree of size n minus 1 instead of a tree of size. Okay. So remove is just notations to make x a leaf, and then a normal DSC splice or remove. So what have we just shown? We've just proven this theorem that the tree implements the sorted set in a base and adding an element, removing an element, and finding an element each take log n expected time. And in fact, if we want to be more precise, they also each take at most 2 log of n plus 2 comparisons. Let's say, use this phrase in expectation, meaning that the expected number of comparisons when we add or remove one of these things is at most 2 log of n plus 2. So that's another way of making a balanced binary search tree is through randomization. So this idea of using these random priorities to build one of these random binary search trees. The first way we saw was through amortization, or what's called partial rebuilding. In scapegoat trees, when a tree gets sort of a bad state, you just rebuild it into a perfectly balanced tree. Here you don't have those terribly expensive giant rebuilding operations. You just have fairly simple add and remove operations that do a few rotations. Yeah.
what's the point of using a tree over a regular?
Or what kind of binary search tree? Well, you can't use a random binary search tree because someone may ask you to insert elements into a binary search tree, not in random order. Right? So, the typical thing is you build a binary search tree because you load some data from a file and you say, let's put all these lines from this file into a binary search tree. And oops, that file actually was already sorted by some other program. And now if you just build a normal binary search tree, you get a new hash. So a tree gives you a thing which looks like a random binary search tree no matter what order you inserted the values, and no matter what you deleted in the meantime. So it's just using this fact of random binary search trees, which you can't guarantee that you're gonna get random insertion orders. So you fake it by saying, well, I'm gonna simulate it, I'm gonna make a tree that looks like I was given a random insertion order. And that's by choosing these random priorities. How do you choose these random priorities? Well, usually you can choose them to be big random integers, so use your random number generator. There is another trick that you can use, which is when you create a node, just a normal binary tree node, it lives in memory, right? So it has an address in memory. And that's unique for that node. No other node has the same address. So I can take the address of that node and hash it. So that takes a unique value and turns it into a random looking value, which that hash value is then the priority that we use. The nice thing about that is you don't need then to explicitly store the priorities because you just have when you need the hash value for a node, it's because you have a pointer to that node, or the priority for a node, you have a pointer to it. You can do the hash value and you're good to go. So you can implement these without storing any additional information that the node except the key. Okay, good. So I said that I hate when topics go across two classes like this. So to prevent that from happening, I'm going to punish you. And we're going to try and not completely prove this theorem, but get a good understanding of why this theorem is true. Why is it that in a random binary search tree, you have this nice property that the depth of a node is not very big? And we'll start with an example. But first, has anyone seen this sequence before? 1 plus a half plus a third plus a quarter plus 8 plus a fifth. 1 over, okay? Anyone seen this thing before? Yeah. So, the shorthand for it is, this is the sum I equals 1 through k of 1 over I. And this number comes up so often, these kinds of numbers, that they have a special name. They're called harmonic numbers. And the kth one is usually denoted by h sub k. Now, what can you tell me about harmonic numbers? Anything? What's that? They don't converge, actually. So if I take that sum off to infinity, I get infinity. Yep. Yeah, so that's another name for it, the sum of the first k reciprocal. So we'd like to know what this thing looks like. H sub k is a funny name. It's not, you don't have a good idea what this looks like. And so one way to do that, when you have a sum like this, is to draw it, and then maybe beat it up with some topics. draw this thing graphically. I have this sum, and I'd like to draw a picture of this thing so I understand what it looks like. So here's a y-axis and an x-axis. They're not uniformly scaled. Here's one, and there's one here. So the first term here, I can represent this as a thing that looks like this. No, it doesn't look like it, but this is a 1 by 1 rectangle. So the area of this thing is 1. So if I count the area of this rectangle, that's the first term. And then the next one is I'm going to a half here. And now this is a 1 by 1/2 rectangle. So this is the second term. Then I go to the third. And then a quarter. So this is a 1 by 1/4 rectangle, 1 by 1/3. So actually the sum that I'm looking at is, when you study calculus, you'll learn that, well, integrals actually, what you're really doing when you're taking an integral is you're drawing a picture like this, but you're making these things really skinny. And here, the function that you're interested in, you're going to be taking the integral of, is 1 over x. So 1 over 1, that's 1. 1 over 2 is 1/2. 1 over 3 is 1/3. 1 over 4 is 1/4, and so on. And so when I take this integral from 1 to k, 1 over x, with respect to x, what is it? What is the graphical picture of that integral? Yeah. So it's equal to the natural logarithm of n, of k in this case, and plus some constant of integration. But graphically in this picture, what does that represent? It's the area under this curve. So it's this round area here. Now, notice that this brown area actually covers all of the rectangles except for the first one. So that says this thing must be bigger than 1/2 plus 1/3 plus 1/4 plus 1 over k. And if we add 1 to both sides, 1 plus 1, that's still true. But then this thing is hk. Hk is less than log of k plus 1. That's because log of k covers all of it except for the first one. And you think that's a good estimate? Is it off by much? Well, what if I just take this curve here, 1 over x, and I just move it over one position to the left? So now it actually starts up here, and ends here, and here, and here, and there. Now the area under the curve didn't change. This purple curve still has the same area under it as before. It's the natural logarithm of k. So this purple area will also be equal to 1 over x with respect to x. Okay? The natural logarithm. Okay. But notice that actually that purple area is contained inside all of these rectangles. So it actually has to be smaller than the area of all the rectangles because it's inside of it. anytime you see one of these harmonic numbers, you can think to yourself, well, this thing is really squiggly like, if you look at these squigs and don't look too closely, it looks like the natural logarithm of k, plus or minus 1. And notice we have things like ln n, 2 ln n plus 2 here. This is where this plus 2 is coming from. We get an answer that is a harmonic number, and then we turn it into something that represents the natural logarithm. Okay, good. Let's just keep that in our back pockets. The harmonic number is sandwiched in between these two logarithms here. Now, let's look at an example. Of a random binary search tree. It's going to be a random binary search tree that contains 6 values. Okay? And in this binary search tree, we're going to search for x equals 6.5. I don't know what the permutation is yet of the 6 numbers that made the tree, but we'll try and inspect it. Okay? And now I would like to know, what is the probability that we visit node 1 when searching for x? All right, that sounds hard. So give me an example of a tree where if we search for x, 6.5, we'll see the node that contains 1. Give me any example of this tree. 1, 2, 3, 4, 5, 6. Yep, if we search for 6.5, we'll see node 1. Give me another example. There's no other trees where you'll see 1? Yep. Yep, 1, 3, 4, 5, 6 looks like this. 2 fits in there somewhere, I guess. Later, looks like this. Then we see node 1. Any other example? Yeah, 1, 4, something. What's common about all these examples? 1 is at the root. Okay, that's kind of boring. Of course, we're going to see it if it's at the root. Give me an example where 1 is not at the root. You say 2, 3, 4, 5, 6? There is none. Wait a minute. So we'll only visit node 1 if it's at the root of the tree. Otherwise, something else is at the root of the tree, right? That something else is 2, 3, 4, 5, or 6. So we put that something else there. I don't know, let's say it's 4. Eventually 1 gets inserted, so it's all 1 is somewhere over here. But when we search for 6.5, we're not going over this tree here. We're going off this way. 6.5 is going to look down here. So we'll never see 1. So we'll only visit 1 if it's the root of the tree. Well, to be the root of the tree means that in this permutation, you have to come first. You have to be the first node inserted. So what's the probability that if we take a random permutation of these 6 items, that 1 is the first thing? It's just 1 over 6. Everybody's equally likely to be the first thing, so it's 1 over 6. Aha. Good. So we actually nailed it. We know exactly the probability that 1 gets visited. How about 2? What's that? is not exactly the same because 2 doesn't have to be the root, right? 2, I mean, here's that tree again, where we'll visit 2. No, no, no. I mean, the probability we visit, just to write it down maybe precisely, probability we visit node 2 when searching for X. Yep. Sort of. And to figure that out, well, 1 is not really relevant to us when we're studying 2. 1 isn't going to change whether we see 2 or not, because if we see 1, well, then 2 goes off to the right of 1, and so does 6.5. So they're both going in the same place. Really, the only important stuff is these guys here. Yeah. Nope. So, what happens if can you give me an example of a tree where I will visit 2, but first I'll visit 4? So is there a tree that looks like this? I'll visit 4, and then I'll visit 2, and then I'll go down and get 6.5. Yeah, the only way that this can happen is if I look at my random permutation, forget about 1, look at the permutation of these guys, and 2 has to come first. Because if any one of these things comes first, out of all of these things, well then, it's going to show up in the tree. Later on, 2 is going to come along and get inserted in the tree. Well, but it's smaller than that, so it's going to go off to the left. And then later on still, I'll come along and search for 6.5, but I'm going to go off to the right, so I'll never visit 2. So this only happens, we only visit 2 if among these 5 elements, 2 is the first one to appear. And again, if I just focus on some part of a random permutation, then that's also a random permutation of those elements. So of these 5, 2 is equally likely, 3 is equally likely, 4 is equally likely. Each one has the same probability, 1 over 5 will appear. All right, now we may see a pattern. How about if we visit node 3? What's the probability that happens? 1 over 4. The probability that we visit 4 is going to be 1 over 3. Probability we visit 5 is going to be half. And the probability that we visit 6 is actually 1. So we'll always have to look at 6 when we're looking for 6.5. We sort of knew that was the case because we know that when we search in a binary search tree, we will see the values of the closest elements on the left and the right. 6 is the closest element on the left. So we'll see it with probability 1. Otherwise it wouldn't be true. Okay. All right. So now let me just say, let I sub I equal 1 if we visit node I when searching for 6.5 and 0 otherwise. And now, number of nodes visited while searching for 6.5 just have to count up. Why? Right? This is just this binary variable that tells us whether or not we visited a node on the search. If we add up all those binary variables, we get the number of nodes we visited in the search. And now we do our usual trick. We're interested in the expected value, expected number of nodes we visit. The real nice thing about expected values is that they're linear, which means that there's expected value of the sum that's the sum of the expected values. So all we need to know is the expected value of I sub I, which we know because we can just write them down, right? Expected value of, for example, I sub 1 is equal to 1 times probability that I sub I equals 1 over 6. Expected value of I sub 2 is 1 5, and so on. So the sum here is just 1 over 6 plus 1 over 5 plus 1 over 4 plus 1, which is the sixth harmonic number, which is less than or equal to ln of 6 plus 1. Okay. Now, nothing special about 6 here. We could have done this for n, and so this becomes n, this becomes n, this thing starts at n minus 1, this becomes h of n, and this becomes ln of n plus 1. So what did we just show here? We just showed that if we take a random binary search tree, we build this random binary search tree, and now we search for the biggest thing, something that's bigger than anything in the tree, then we know that we'll visit ln of n. At most, in expectation, we'll visit ln of n plus 1. So the right path in this tree contains at most, in expectation contains at most 1 n plus 1. Now, that's not the same as this term. This term says 2. But this term is supposed to hold for any value of x. Not just the value of x that's bigger than everything in the tree. But to prove this term, it's basically the same thing. You just have to look at, right. So here we're counting all the nodes, basically where the search path goes right. And, well, that's because this node is bigger than anything in the tree, so the search path only goes right. But in general, the search path goes left and right. And so to make this work, if you're searching for x, you have to look at all the values 1, 2, 3, 4, up to floor of x, and on the other side you have to go to the ceiling of x, all the way up to n. But now the same arguments work. What's the probability, for instance, that I will see the node 4 in this thing? Well, that will only happen if among all these elements, 4 is the first one that's inserted. So you get a 1 over I for like a 1 over x minus 4, and you get a bunch of these things. In fact, on the left here, you get something like the harmonic number of x, and on the right, you get the harmonic number of n minus x. And, well, each of those is less than or equal to harmonic number of n, plus the harmonic number of n, which is less than or equal to 2 times the ln of n plus 2. And that's where this theorem comes from. You can read the details in the text if you want, but basically the idea is if X sees one of these nodes, it's because it was the first thing that was inserted in this binary search tree, inserted before anything else that would have separated it from X. And so as you get further and further away from X, you're less and less likely to see those nodes. And that's quantified by if you're right inside X, the probability is 1, but if you're 2 away, it's a half, and then third and fourth. All right, so that's a good place to leave it there, and then we start on a fresh topic.
Is it expensive? It was like, I don't want to use that today.
To be honest, I don't want to decide.
He was trying to add you guys look at this.
某人今天看什么心情？
I'm glad you know if you want that for me, it's
Well, I don't really want to give out the midterm because it's hard to come up with these multiple choice questions once you show them. The final test will cover